Well, hi there. It's Miss Motzi, and this is Geosystems. Today is Monday, April 23rd, and today we were learning about the continental drift theory. Let's take a look at our agenda for the day. This is Geosystems. Today is Monday, April 23rd, and today is a B day. Our objective is I can list the three tectonic plate boundaries and describe their features. On our agenda, we had a short video at the beginning of class on Alfred Wegener, who was the founder of the theory of continental drift. We went into some quick notes on the continental drift theory, especially looking at the pieces of evidence that Alfred Wegener put forward for his theory of continental drift. And then we moved into an online activity on plate tectonics, looking at the different boundary types. We had an exit ticket today on Google Classroom on plate tectonics. You have homework. Your homework is your SOL Week 3 review assignment that is due on Friday, April 27th. And if you didn't finish the plate boundaries worksheet in class today, that's due on Wednesday, April 25th. Here's a quote from Alfred Wegener himself. "We are like a judge confronted by a defendant who declines to answer, and we must determine the truth from the circumstantial evidence." That's what we were doing today. We were looking at the circumstantial evidence. So let's go ahead and look at our notes again. Look at those 5 different pieces of evidence that we talked about in the notes and that you wrote down in your graphic organizer that we had for the notes today. So here we are at the first piece of evidence. The fact that the continents on Earth seem to fit together like a jigsaw. So you can see in this animation here that South America and Africa, they seem to almost fit together perfectly, as if they're puzzle pieces. That was Alfred Wegener's first piece of evidence in support of his continental drift theory. Here's his second piece of evidence. The fact that fossil patterns across continents were matching. So you can see here, when you put all these continents together that are pretty far apart today, they seem to match up perfectly. So you're piecing the continents together like they're a puzzle piece, and then you see that the fossils seem to piece together correctly as well, especially this green swath right here going across all 5 of these continents of Australia, Antarctica, India, Madagascar, Africa, and South America. The third piece of evidence is similar to the fossil evidence, but using rocks. So there are similar rocks in Brazil and in Africa. And not only are the igneous rocks similar, but they also, after using radiometric dating on the rocks, they found that they have the same age of 2.2 billion years old. That's the third piece of evidence. The fourth piece of evidence that Alfred Wegener used was that there's a matching mountain range going across these continents that at one time must have been together. And so here's a picture of that. You can see this is almost like a zipper opening up all the way from Scandinavia and Greenland through Scotland, Ireland, Iceland is in here, and then coming down through the west coast of Africa and North America. The final piece of evidence is paleoclimatic, and paleo means old, climatic means what is the average weather conditions. So when you look at this here, you can see that there was glacially transported sediments of the same age in southern Africa, South America, India, Australia, and Antarctica. You can see that Alfred had a number of different sources for his evidence for his theory of continental drift, but his theory was widely rejected at the time. So he had these 5 pieces of evidence, like the puzzle piece fit, the fossils going across the continents, the rocks of the same type and age going across the continents, the mountain chain that's like a zipper going across 2 continents on continents that are very far apart today, and then finally the paleoclimatic evidence as well. Another thing that you did today was looking at the different boundaries. So there are 3 main different boundary types. You have divergent, where the plates are moving apart, transform, where the plates are moving past each other, and convergent. Now, convergent has 3 different subcategories, and I want to take a second to look at those different subcategories. So here are the 3 different types of convergent plate boundaries. And hopefully you remember from last class when we did the layers of the Earth that there are 2 different types of continental crust. There's oceanic crust and there's continental crust. When they collide, different results are going to occur depending on whether or not you have ocean to continental convergence, ocean to ocean convergence, or continental to continental convergence. So in this top picture, you see you have an oceanic crust on the left-hand side subducting, converging, moving toward and under the continental crust. So first of all, the oceanic crust is subducting underneath because it's more dense, because oceanic crust has minerals that are more like iron-rich minerals that have a higher density. So you have the oceanic crust subducting underneath the continental crust in the top diagram. What are some of the features that occur from that? Well, you get a trench, like you can see where the subduction occurs. You also get some volcanoes, and those volcanoes form what's called a volcanic island arc. You get a whole series of volcanoes, volcanic islands, or volcanoes along the continental plate here. They are not islands, I misspoke. So when you have oceanic to continental crust, these are not islands. These are actual volcanoes, like a volcanic mountain chain. This is happening right now in the Pacific Northwest. So when you think of Washington State and Oregon, you want to be picturing this top diagram right here. Now the middle diagram is a little bit different. This is ocean to ocean convergence. So this is the case where you're also going to have a trench where the oceanic plate subducts underneath another oceanic plate, and you're also going to have volcanoes, but those volcanoes are going to be in the form of islands. So you're going to have volcanic island arcs forming. And then the final type of convergent boundary is continental to continental convergence, and you can see that in the bottom diagram here. When you have 2 continental plates converging towards each other, neither one wants to subduct underneath the other. So what happens in this case is you get really, really high mountain chains like the Himalayas. You don't get any volcanoes at all. You get some earthquakes, but you don't get any volcanoes. That's it for today. Everybody have a great Monday, and I will see you on Wednesday. Don't forget to do your homework. Don't forget to do your week 3 SOL packet. Don't leave it till Friday. Nobody wants to be doing JLabs on Friday night. And don't forget, if you did not finish the plate boundary worksheet in class, you want to finish that up for homework. All right, I'll see everybody soon, and next class we are going to be learning about, we're going to learn more about seafloor spreading. We talked about that a little bit today with the paleomagnetism. All right, everybody, have a great afternoon. I'll see you later.